name is Odelma, and in this seminar I will present the work Computational Modeling of Hypersonic Nozzle Flows in Thermochemical Non-Equilibrium. During this presentation, I will point out the objectives of the work, the mathematical formulation, the description of the test cases, a discussion of the results, and the general conclusions. Wind tunnels are one of the most important tools in aerodynamic research. One of its main components is a convergent-divergent nozzle, which is responsible to accelerate the flow to reach high Mach numbers at the exit and to simulate the flow conditions experienced by a spacecraft when re-entering the atmosphere. It is important to understand the phenomena that occur inside the nozzle to have an accurate prediction of the flow behavior at the test chamber and to have a good characterization of the flow. This is why the computational modeling of hypersonic nozzles in thermochemical non-equilibrium is one of the objects of this work, and also to investigate how the stagnation enthalpy at the inlet of the nozzle will change the quality of the flow. When investigating, we found that there was no studies on how the catalytic activity at the nozzle wall would influence the flow properties at the nozzle exit and test chamber. This is the reason why we investigate how the catalytic activity, that is, the reactions that occur at the nozzle surface, would impact the flow properties. During the expansion of the flow through the nozzle, the translational and rotational energies drops abruptly, while the vibrational and electronic energies remains high at a temperature that is close to the nozzle reservoir temperature. This non-equilibrium state could prevail through the nozzle and change the quality of the flow at the test chamber. So, to model this non-equilibrium, non-equilibrium Navier-Stokes Fourier equations are solved according to Parkes two-temperature model. That is, the translational and rotational energy modes are considered to be in equilibrium, deriving the transrotational temperature. And the vibrational and electronic energy modes are considered to be in equilibrium, deriving the vibroelectronic temperature. For that reason, in addition to solve a total energy equation, we also solve a vibroelectronic energy equation and a total mass conservation equation, a mass conservation equation for each species, and the three momentum conservation equations. The source term here corresponds to the mass production of species due to the reactions, and also the term responsible for the energy transfer between the vibroelectronic and transrotational energy modes. Three different nozzles with different stagnation enthalpy conditions were used in our study. The first table shows the stagnation conditions at the inlet of each nozzle in terms of specific enthalpy, temperature, and pressure. At the inlet of the nozzle, due to the high density, the flow is considered to be in thermal equilibrium. That is, the transrotational temperature is considered to be equal to the vibroelectronic temperature. The second table shows the flow composition in the inlet in terms of the species. Due to the high enthalpy conditions at the inlet of nozzle 3, the flow at the inlet is partially dissociated, and the nozzle 3 has three configurations, and each configuration, C, D, E, and F, corresponds to a specific design Mach number and also a specific expansion ratio. The figures show the distribution of transrotational temperature, static pressure, and Mach number ratios between equilibrium and non-equilibrium conditions along the nozzle center line. We can observe a consistent behavior between the results for the three nozzles, with the temperature ratio increasing along the nozzles and also the pressure ratio increasing and the Mach number ratio decreasing. The temperature is higher in the equilibrium condition because all the enthalpy is converted into the kinetical energy, while in non-equilibrium condition, there is energy that is converted also in vibroelectronic and chemical energy. The pressure in its term is consequently lower for non-equilibrium condition, which is according to the equation of state. And Mach number is the opposite. It is lower for the equilibrium condition. since it's inversely proportional to the temperature. In the table, we can see the difference between equilibrium and non-equilibrium results for the temperature, pressure, and Mach number at the exit of each nozzle and the corresponding expansion ratio. We found that the nozzle 2, which has the higher expansion ratio, is also the one with the higher difference between equilibrium and non-equilibrium results. Here, it's possible to observe that the Mach number is higher for the non-equilibrium condition. Immediately after the throw, the Mach number for the non-equilibrium condition grows more rapidly and reaches higher values. The temperature distribution graph at the right shows the rapid expansion from high temperature that causes the drop of the transrotational temperature. It drops abruptly, while the vibroelectronic temperature remains high and freezes inside the nozzle around 0.18 meters, which is represented by the dotted vertical line. It corresponds to the freezing point. In order to understand the enthalpy effects on the thermochemical non-equilibrium, 3 stagnation conditions for nozzle 2, which is the nozzle with higher expansion ratio, are used. These figures show the non-equilibrium degree for temperature, pressure, and Mach number along the nozzle 2 for the 3 stagnation enthalpy conditions present in the table. As we can see, before the freezing point, which is the dotted vertical line, the non-equilibrium degree is higher for the lower enthalpy condition of 4.92 megajoule per kilogram. And this is because the relaxation time, which is the time required for the vibroelectronic energy to equilibrate with the transrotational energy, is inversely proportional to the pressure and is highly dependent on the temperature, as we can see. So after the freezing point, there is a change in the curves, and the non-equilibrium degree is lower for the lower stagnation enthalpy condition and is higher for the higher stagnation enthalpy, for pressure and for the temperature. For the Mach number, it's the opposite, because the Mach number is inversely proportional to the temperature. Also, we can see that after the freezing point, since there is no exchange between vibroelectronic and transrotational energy modes, the pressure contribution is meaningful, and the non-equilibrium degree is higher for the higher stagnation temperature condition, which also corresponds to the higher stagnation enthalpy condition. In this table, we can see the flow properties at the exit of the nozzle 2, the nozzle with the higher expansion ratio, for equilibrium and non-equilibrium conditions and the difference between them. It is possible to observe that for all the properties, the non-equilibrium degree increases with the increase of stagnation enthalpy. For example, for the pressure, the difference between equilibrium and non-equilibrium is of 28% for a stagnation enthalpy of around 5 megajoule per kilograms. It's 30% for a stagnation enthalpy of around 6 megajoule per kilogram. And if we increase the stagnation enthalpy to 7.56 megajoule per kilogram, we have a difference between equilibrium and non-equilibrium of 35%. Here we have some of the results of the investigation of the impact of the wall catalytic activity in the flow field. 2 extreme conditions were considered: a fully catalytic wall, represented by Fc, and a non-catalytic wall, represented by Nc. In fully catalytic walls, all the atoms that reach the nozzle surface are recombined into molecules, while in a non-catalytic wall, there is no recombination reactions occurring in the nozzle surface. So the first graph shows the heat flux distribution for non-catalytic and fully catalytic walls, and also the ratio between them. As it can be seen, the heat flux is higher for fully catalytic wall with an average ratio of around 2, which is consistent with the values obtained for entry vehicles. The next two graphs shows the transrotational temperature and the pressure at the exit of pressure at the exit of nozzle 3, which which has three configurations for non-catalytic and fully catalytic surface, and also the ratio between them. We found that the temperature and pressure ratios between fully catalytic and non-catalytic surface increases along the nozzle. It increases from the nozzle C to nozzle F, which also corresponds to an increment of expansion ratio. So in the table, we can see in more details the relation between expansion ratio and the difference between the flow parameters for fully catalytic and non-catalytic surfaces. Except for the vibroelectronic temperature that freezes inside the nozzle, the difference between the flow properties at the core flow increases with expansion ratio. For example, at the exit of nozzle F, the difference between fully catalytic and non-catalytic results is of 1.5% for Mach number, 2.9% for the transrotational temperature, and 8.2% for the pressure. So after this analysis, we can conclude that the thermochemical non-equilibrium affects the flow properties at the nozzle exit and the test chamber by dropping the transrotational temperature and the static pressure, and also increasing the Mach number. Also, we could conclude that the non-equilibrium effect increases with the nozzle expansion ratio, and higher stagnation enthalpy conditions at the inlet of the nozzle will lead to an increase of the non-equilibrium degree at the exit of the nozzle and also at the test chamber. We also found that the catalytic activity at the surface of the nozzles will change the flow properties at the nozzle core flow and also at the test chamber, and this impact will be intensified for higher expansion ratios. Thank you so much for your attention, and see you next time.